So, and thanks to Neb, who asked me to say, then we forgot to talk about a title, so you put in a title for me, and that actually really helped me deciding on how I would finalize putting this talk together. I'm going to mix a little bit my own personal research just at the beginning, and then talk more about both the history and where we are at. And apologies to a few of you who may have seen part of that before, for instance, last year when I got the opportunity to talk at the New Zealand Control Release Society meeting, in Dunedin. So I'm a chemist by background. It's good to also see how many chemists are involved here. It's a very good thing. Nothing wrong with that, right? Let me see what... Oh, that way, okay. That's counterintuitive. Right, so it's just a chemical molecule, right? It's actually fascinating when you think about mRNA. It's a molecule that has a molecular weight, say in the case of the spike protein, well over 1 million. As a rule of thumb, your mRNA molecule is 10 times bigger than the protein it codes for, right? I mean, actually just, oh yeah, of course, 3 bases, 1 amino acid, you do the numbers. But it's still a molecule. And actually, one of the social media battles I'm having now with is in relation to, I think the European Medical Authority and some other organization are going down the wrong track because they're trying to force mRNA to be classified as biologics, which to me doesn't make any sense. It's just like they can't get it. It's a molecule. Like we don't need even to use cells to make it, right? Okay, what's the other reason why we think RNA is an interesting molecule? It's not only because it's much easier to make and work with than, say, other molecules, other identities we might make into vaccines and whatnot. I love this, Dabe, from your old boss, the Moderna. I love this phrase. Actually, it's always simplification, but if you think of DNA as the hard drive, right, and you think of the ribosome as a printer and spits out some pages, RNA is a software that comes out of the DNA, and one part of the software is the mRNA. Now, I want to emphasize mRNA is just one part of it. It's less than 2% of the genome. And that's what personally interests me much more. What about the other 98% of the software that doesn't go to a printer, but go to all the other components of the cell and is a structure element? And I think that's where the future opportunities are in this space. And as I say, from a chemistry background, again, these are molecules. They have real three-dimensional structures. Yes, they are flexible. And as Matt Disney, who I greatly admire at the Scripps Institute in Florida, has pointed out and in fact demonstrated with his own startup companies, you can easily use med-chem approach to come up with therapeutics that modulates interactions of these RNAs with other molecules. So that's sort of my inspiration. Also, before I forget, I just want to acknowledge the research group, because they're the ones who do the real work. I don't do any much. And the funding agencies. And my own research group, as I say, we've been, I come from an organic and supramolecular chemistry background, but we've been in nanomedicine and technology for over 10 years. And you can kind of see that sort of still a theme, delivery, both for polymer systems and now LNP, with great interest in materials for controlling cell growth. But it was kind of out of that gel work with peptide that about a decade ago, I got dragged into the RNA peptide world. And the other component there is that my own PhD work back at Sydney over 20-something years ago was on cell-replicating molecules, i.e. the origin of life. So I always wanted to work with RNA, eh? And then I came across this thing, liquid-liquid phase separation, which, well, I mean, for us chemists, that's a pretty well-known concept. But when you think about it, you can also get it in aqueous systems. And this, I really need to find a photo from Iceland. This is from Alaska. But you will see this here also on the South Island. It's a glacier river running into the ocean, right? And you get these boundaries. They can go for miles. And the reason is that you've got salt water with one chemical potential and fresh water with clay, which is like a polymer. And these things don't mix easily, so you get a phase separation. It's kinetic, though. They will mix in the end. But in the cell, we also see these kinetically phase-separated systems. And it was through a friend of mine at UNSW who pointed me to the work of Arthur Fox that I started, hey, wow, this is really, really cool. And she discovered paraspeckles nearly 20 years ago. Not the very first of these membraneless organelles, but almost the first, but also more importantly, they're now probably the best characterized. And through the work that Archer, and particularly her collaborators in Japan, have done, we understand the structure of these better than most of the other condensates. So in this particular case, there is a single non-coding RNA. It's very large. It's 23 kilobases. That forms complexes with several proteins that forms these powder speckles, which in turn are very important in gene regulation and God knows what else. And again, for chemists, the interesting thing here is that these proteins often have either large intrinsically disordered regions and or these sort of prion-like repeat sequences. And this may indeed have consequences beyond sort of just fundamental structural biology and chemistry. There's in vitro evidence at least that some of these droplets under certain conditions form fibers. So the real question is this the real in vivo cause of diseases where we see the pathology through protein fibers? These proteins initially have a functional role in some sort of condensates, and when things go wrong, they start to precipitate. Who knows? But personally, I think this is the key to unravel the mystery of how these diseases actually originate, because the conventional amyloid hypothesis is clearly, utterly wrong. You can ask the $100 million worth of investors that lost their money on that, why, right? So we started this finally sort of 5 years ago, and we did something very simple, you could say stupid. We made pentameric RNA, really simple RNAs, and really short peptide, and say, hey, what happens when you mix them together? Well, we get droplets. Isn't that cool? And they even look different with some slight modifications in your RNA. Now, I'm not going to go through all of it, but just to sort of point out that, again, in the proteins in nature, you often see these, as I say, repeat motifs. One of the most common one is RGG, so arginine diglycine. And then Annika, she designed this very short peptide, it's sort of an RGG motif with a phenylalanine on it, and until we can put dyes on. And then we did a really simple experiment. We made 2 decamers. One is just AG, 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 and one is CU, CU, CU. They both have the same negative charge. You mix them with the peptide, things should be the same, right? And you can see here when they're labeled, they look pretty cool. No, they're not. Because it's also the aromatic interactions that matter. So in this particular case, purine-rich RNA forms much better condensates with this particular peptide than the pyrimidine. And this is basic physical organic chemistry. There's some sort of a cationic pi interactions that are important here too. We got evidence of that now in some other work, but as you say, this is just to say there is some fascinating stuff going on in these systems. And as a last example of that is work I do in collaboration with Felix Risotto, who, by the way, last week won one of the 2 Moderna 2024 Australia Future Fellowship, Australia Fellowship. A really talented gentleman who works in the sort of DNA, RNA, origami field. And the common interest Felix and I have are also in, when it comes to the real structure of RNA, it's more than just what's on Crick. It does include so Hook-Sting pairing, for instance, right? And we know they can create some funky secondary structures. So, and what Felix has shown, like, well, I guess was known, you can often modify these by modifying the buffer. So what Lachlan, who works with us, did, he made 2 RNAs. He made both 21 mers, and they essentially complement each other. And one forms a quadruplex. Yeah. And the other forms a maybe slightly less known I motif, where you get these cytine-cytine pairs, but only if the pH is sort of down to about 4. And then what Lachlan did was to, again, make a short peptide, sort of RGG-inspired peptide, and we just want to see what happens when we mix these with either the quadruplex or the I motifs. And we do binding studies. Some of you know that's one of my sort of hobbies, right? And essentially, what happens is, first of all, that if we look at the quadruplexes and RNAs here, the peptide binds much more strongly to a folded quadruplex. You can fold it with a potassium and you unfold it. And it also binds stronger to the DNA. So again, there's no charge differences. It's just that one hydroxy group, right? And likewise for the I motif, you get much better strong binding with the RNA and the DNA. Now the stoichiometry is 2 to 1. I'm not going to show you this here. It means that this is the quadruplex. There's one peptide on each side. We see this now from NMR. And more importantly, it's actually the peptide essentially chaperones and folds the unfolded RNA. And yeah, so, and we can also show the pH dependence. So that was sort of my whirlwind tour to sort of not just talk about manufacturing, politics, and God knows what else, but also tell you a little bit about the research, because after all, I don't know about you, but I am still an academic. That's what keeps me motivated after many hours of boring meetings, to go back in the lab and see something like this from very talented people I get to work with. But there is a bigger message to this, which is, I think, as fascinating as mRNA is, and vaccines and all the therapeutics, I actually think the real opportunity is downstream in understanding how we modulate, control the 98% of the RNA. It doesn't get transcribed into mRNA, and that includes controlling and understanding its structure. So it is always back to the basics sometimes too, with structural biology and chemistry. Right. So, coming back to the ecosystem development, actually thanks to a gentleman somewhere over there in the hills, Justin Hodkins, and others that got involved in, for some time in solar cell work, trying to make some plastic solar cells. I got familiar with this whole idea, which apparently comes from NASA, of technology readiness level. And it is a helpful concept. I mean, it's simply saying, here's your idea, here's your prototype. And this is from some European agency mapping it in the pharma space that, oh, here's your idea, this is roughly in vitro, this is in vivo, the valley of death, because things get very difficult and expensive and hard to raise funding. And these are your phase 1, 2, 3 trial, where it gets easier to raise funding, but you still haven't got your prototype. A problem for us in Australia, just like here, is that pre-COVID in the RNA space, we had no support here, and we had no capability either to do preclinical scale-up, not to mention GMP. So any good ideas that might have been developed in Australia would normally end up somewhere else fairly quickly. Now, there was 2 exceptions to that, actually. One was CSL, and you'll see this in a moment again later on. CSL actually happened to have purchased some very valuable IP on mRNA from Novartis in 2014. Which in a roundabout way made them one of the oldest and the most advanced RNA companies in the world. But whether they did much with it those few years in between COVID and 14, that we don't quite know. PYC is much more interesting. This is a company that sort of comes out of the work that's been going on with Sue Fletcher's in order in Perth for over 20-something years. And they use cell-penetrating oligoconjugates to try to treat eye disease. So this is quite an interesting technology, and they're in phase 1 trials with this. Okay, but yeah, in terms of research, this was the support, and that was in both countries, right? And as I say, Archa in some ways helped chaperone this group. Well, Archa and Nigel. Now, Nigel is a native of yours. He's from Timaru, I believe, but he's been in Australia for a couple of decades. Now, we kind of didn't know each other, all of us, but yeah, we self-assembled on Zoom, and by accident became the kind of lobbying group for RNA in Australia, because at that point in July 2020, Colin was working on mRNA vaccine. Some of us were trying to raise the interest in, as you will see in my own case, but no one really paid attention to us. That was the reality. I don't know, it was slightly different here, but it wasn't until October, November 2020 that the conversation started changing in Australia. And there were political and technical reasons for that. But yeah, and then we expanded the group, and thanks partly to Peter Davis, who encouraged us to include people from a few of the other states and from New Zealand through William. And it was a great group to be part of. We kind of, I guess we sort of, we're there still, but we haven't done much lately. But this was a way of having a community and a bit of a sharing of process and information between what to the external world always looked like completely competing programs. But they weren't, maybe. Yeah, and say team sort of took Trent's role when Trent moved into industry in Brisbane. My own journey, as I say, is like everything else, very non-linear, but it starts with a nanomedicine center we set up at the UNSW 15 years ago, and there was an ARC center in similar field across the country a few years later. Albert was a key person for me because he brought RNA synthesis to our department. Yeah, and that's why pre-COVID I started talking to our chief scientist in the state. Australia is funny that way, that often these programs are driven at the state level and the federal level. Well, I should say what I probably learned is the states are often more innovative when it comes to this than the federal government. And yeah, I raised the issue because I knew these people, to them in July 2019, I think we should invest in RNA. I thought, well, that's an interesting idea, but then nothing happened, of course. And then I started getting phone calls as 2020 rolled on, and ended up at stage with the Premier. So what the government there in Sydney decided to do was to make an investment in collaboration with universities, and this is somewhat the unique feature of that program. We set up initially also a pilot program between 5 of the universities supported by health, And then each university does whatever it wants to do. And in our case at the UNSW, the university, not the state, invested in the institute I lead. And so did ANU, thankfully, soon after that. But the investment from the government is twofold. It is in a small-ish, but not that small actually, CDMO facility for providing materials for clinical trials for any customers who want to use it. But also to support a more comprehensive R&D push in the state over 10 years in collaboration with other jurisdictions. So that's sort of the nutshell of the program. We started, say, in 21. It's taken a while to sort of do things sometimes. I learned governments are not much faster than universities, and that's not a compliment. But we're there. And as I say, the CDMO is actually owned by the government, but then rented to this company that won the tender. And as I say, it's application agnostic. It operates like a normal CDMO. And I say the more important bit was this 10-year investment, where we got the government. It wasn't easy to agree to a 10-year investment. In fact, it was funny because, I don't know if you've seen it, Julie, the politicians were fine with it. It was the Treasury bureaucrats who really were not happy about the idea of locking in fund for 10 years. And we said, you can't do anything in bio for less than 10 years. And it's like, nah. But then, yeah, the Treasurer had to have a fight with his own people. I kid you not. It was an eye-opening experience. I don't know if it's the same here. But it worked, right? And it's now organized through an organization that was set up kind of independent of both the state and the universities. So those of you who may be familiar with CRC schemes in Australia, it's a similar kind of not-for-profit model, but it means like it kind of off hands from the university and the state, but it still has the mandate of supporting work back through this fund. And yeah, we broke ground for the facility only 2 months ago, so that's me in the corner. I do know, I think, how to hold a shovel after working on a farm. And Susan next to me, she was the chair of the RNA Australia. And then, yeah, I just saw photos from this now. They've pretty much finished with the pouring the concrete for the base. So it's all happening now. The other thing we did in Australia, sort of to bring people together, was that NCRIS, which is our National Collaborative Research Infrastructure Scheme, has one of the component of NCRIS, Therapeutic Innovation Australia, which supports accelerating people in small molecules, cell therapies, and proteins. And they basically now established a fourth component, which is RNA products. And that's linking together the facilities that two of them were already quite operational for a couple of years, TIMS, UQ, and ours at UNSW. Colin obviously been doing for much longer, but he's now also set up a bit of a more sort of a customer-facing, I should say, facility perhaps. And Arch raised some funds in Western Australia to set up a facility there, which also NCRIS is now supporting. And what we're trying to do, and it's sort of important for the Mulligan and Ferrier Institute here, is that some of the stuff these four places are doing is same, but we're also kind of specializing in what we think we're good at. Say, at UNSW, we focus on the oligo and scale-up and QC, the QQ1 more on the mRNA design, Colin on the lipid formulation, and Artes moving towards high-throughput mRNA for cancer application. So there's a bit of a specialization going on too, but also sharing protocols, and we're all under fully running a pretty much full capacity. So that's kind of the landscape, and I'm including, of course, the platform here, which I think is really important, and I've been so glad to see also on both sides of the ditch how there's been a lot of connection made between the platforms and programs. I mentioned most of this to say there's also the Innovation Hub between Monash and Melbourne. It's quite an important one. And then in the ecosystem space, I color-coded this deliberately. So the blue ones are the outpost from the large companies, and they may or may not be setting up manufacturing. In most cases, they will only probably work with people on their own term. Sarah and I had a discussion about this earlier with BioNTech, but I think we'll see exactly what their model is. Clearly with Moderna and CSL, if they go into, Moderna will, CSL might go into GMP. They will only do it on their terms. Sanofi might still do that. The red ones are the more I would call independent / conventional CDMO. Not that all of them are going GMP, but I would say most of them have ambitions to do that. And yeah, I don't think it's a bad thing, by the way. I think it's a good thing that we are doing this because it's sort of a bit of a risk mitigation. Having a few of these options and different business model actually is a risk mitigation in its own right. Some of these initiatives or factories will fail, not because they were a bad idea, but because of some other factors. Companies going broke or the wrong people managing at the wrong time. So having a bit of a redundancy here is actually not such a bad thing, okay? And as I say, it also helps having a very strong environment of suppliers and engineers and so on, that they can go and service things in several facilities. And as I say, what's happened there? For our institute, just briefly, one of our highlights is the fact that, I'm going to go the other way around before I talk a little bit more about what we're doing at UNSW, but I always feel like one of the best things we've done is all the international connections we are making. We have particularly strong relationship building now with McGill, but also with the New Zealand one. That's one I'm very proud of. I'd say two other things I highlight we're very interested in is the rare disease space. It comes back to the sort of N=1 discussion, but not in cancer, but more in rare disorders, neurological conditions and so on in newborn kids, which is probably more an ASO issue. And then workforce training. And this is across the entire Australasian space, of course, if we're going into GMP. And there's several things happening in Australia in that space. It's not just RNA. There's a big protein facility coming online for CSL. Thermo Fisher expanding. There's a viral vector facility being built in Sydney. So there's at least in Australia, there's quite a demand for GMP workforce. And some of that, and this is something us in the university realize, it's not our job to do. It's actually more like what we call in Australia TAFE. It's the vet sector. And we need to support the vet sector to do that training, because it's not all university-based people that need or want into these facilities. Okay, so briefly, if I wrap up with our institute, as I say, we were set up in 21 in part in response to this whole investment from our state, but we built on, as I always say, you stand on the shoulders of giants, and in our case, we had been running for a long time a nanomedicine center, one of the oldest in this part of the world. Kirby Institute, very big in infectious diseases, particularly blood-borne diseases. Started its life as an Australian HIV Institute. We got a very strong and successful genomics center, sequencing. And then Children's Cancer Institute, which has been doing work on developing siRNA therapeutic for over 10 years and very active in the nanomedicine space. So we put the institute together in terms of research with focus sort of very broadly biology, medicine, and chemistry. I should mention also it's a bit unique compared to many other similar institutes and centers that we have a lot of chemists and engineers involved. And, but I think it's important, like we need to bring these three fields together, and I would say engineering is kind of the fourth, it's like a technology underneath all of that. And in our research, we focus on RNA interaction, that includes the condensates, delivery, that's probably the biggest one, a lot of polymer people and whatnot involved. Sensing was some great programs in liquid biopsy and novel nanosensors. And then manufacturing, and it's probably particularly our facility, more on the quality control and analytical side. Priority in health, infectious diseases, oncology, rare genetic disorders, and the future, I think, in neurological. So just briefly about the facility, we have now 20 staff. We got synthetic oligos, clean room, analytical capabilities. We can scale up, and we are still the only ISO 9001 certified facility of this kind in, Australasia, I believe. I was just saying to Rebecca or someone, that comes actually at a price. It does take a lot of effort, time, and money to do that, and it also slows you down in some ways. So one of the things we're working through now is how can we also set up processes which are simpler and not under the ISO 9001, so we can do a higher throughput with some of the smaller scale projects. But yeah, we offer the whole range, synthetic, pDNA, RNA, and just to sort of wrap up here, two examples. So my baby, the LCMS, like we can sequence oligos, and this is really powerful too for quality control. And just as a last sort of research example, we can actually use this to analyze the Pall tail. So what you do is that you use you cleave it with an RNA T1, isn't it called? RNase T1, sorry, I'm losing my voice here. And then you pull down these poly A tail to poly T, oligo T, and then you throw it in the mass spec. And what we see are the two different tail lengths in this case. And we can analyze the distribution by mass spec, because this is, in this case, it's not homogeneous. So that's just to give you, and this is just to give you a snapshot of all the QC methods that we can or are thinking of developing. This is from the Pharmacopoeia. And some two highlights, as I say, are collaborating with TPA in Boston and DPI on emergency response for animal diseases. We're scaling up TPA's project. I'm also dealing with regulatory authorities, and it's quite a story. I was interested in your talk earlier. I don't know how that's going here, but we have to educate them on everything. And yes, and also avoid the brown snakes there on their sheep farm. But yeah, we gave our first batch to them in March. And then also, Philip, in relation to your talk, collaboration with people at Kirby and Macquarie University about inhalable LNPs as an antiviral, so it's using siRNA. So similar but different from the talk that Philip, I can't see where Philip is, gave. And that's going quite well. We're already in vivo with that. And yeah, just very quickly, this is just to show the diversity of projects we do. We do quite a lot in the oligo, probably more than half what we do there. And probably 30–40% is outside UNSW. And some of it goes up to TRL5. So I'll leave it there. I know I'm over time, but thank you again for your kind attention.